አይ ጋይስ ይሰማችኋል? የእናንተ ሚውት ስለተደረገ አይሰማኝም። ኤፍሬም ይሰማሃል? ከክላስ ምንም አይነት ድምፅ አይሰማኝም።
ሚውት ሆኗል መሰለኝ። ሚውት አድርጎት
ሚስ ላይ ናቸው። ያ አትሊስት የሚሰማቸው መሆኑን ኮንፈርም ቢያደርጉልኝ መጀመር እንችላለን።
ኦኬ እሺ።
አይ ቲንክ ዲስኮኔክትድ ሆነዋል። አሁን አይታዩኝም። ጆይን አድርገው ወጥተዋል ተመልሰው። ክላስሩም ያለ ኤልያስ ከተሰማችሁ የእናንተ አይሰማኝም። ሚውት ላይ ስለሆናችሁ ይሁን አይሁን አላውቅም።
ሙት ላይ ነው
እንጂ ይሰማችኋል? የሆነ ሙዚቃ ይሰማኛል። ሙዚቃ ነገር እንጂ ሌላ ድምፅ አይሰማኝም።
አይ ይሰማል ግን
ይሰማሃል አንተ? ኦኬ ኦኬ። ክላስ ውስጥ ያላችሁት ከተሰማችሁ መጀመር ይችላሉ።
አሁን ይሰማል?
ኦኬ ይሰማኛል። የኔ ይሰማችኋል? የሆነ ፊድባክ አለው። የኔ ከተሰማችሁ ችግር የለውም። ሁሉንም ሚውት አድርገን መጀመር እንችላለን። ኦልራይት አሁን ይሻላል። ያ ኦኬ All right, I'm hoping everybody can hear me clearly. So let me know if there are any issues with the audio, but otherwise, I think it's being recorded as well. So you can probably go back and watch the video recording at some stage. Okay, so today is going to be probably our last class as far as I'm concerned anyway. So it looks like we probably covered most of the content we planned. Unless you guys have specific topic to be discussed, I will probably conclude my class today, and we'll be talking about classification. Okay, so we talked about free settling and hindered settling last week, and so how we could apply those in classification and screening of minerals. And from your other classes, you might also have seen some classifiers. So I'm not going to talk in detail about the different types of classifiers for today, but I will quickly mention some of the ones that are being commonly used in the mineral processing industry. And in particular, I will talk about hydrocyclone in a little bit detail because most operations use hydrocyclones. I think pretty much everywhere I went, I see hydrocyclones in action. So some of the other classifiers are less applicable in mineral processing, but hydrocyclones are by far the most common. So we'll probably spend more time talking about hydrocyclones for today. Okay, and we started discussing how we can assess screening performance last week. So we'll talk about that a little bit, and we'll do an example on already provided data. So if you have a classification happening and you collected data from the underflow and the overflow, how do you assess the performance of a classifier? How do you know whether the classifier is working at the required performance level or not? And we'll do a couple of examples on that to see how that's applied. And we'll also see a couple of hydrocyclone models. Maybe this may not necessarily be what you would need to know, but I just want you to understand there are a number of models out there that we can use to predict performance of hydrocyclone. Also, the models can be used to design hydrocyclones and even somehow get an idea of how many hydrocyclones, for example, you would need in a typical operation and things like that. Okay. So in terms of classifiers, probably there are a few different types. So the main ones are classified depending on how they actually work. So for example, in sedimentation classifiers, obviously you'll be dealing with fine material, and this fine material, say about 100, 150 micron material, you want to split it into very fine particles, say less than 20 micron, and coarser particles. So to be able to remove the finest particles into an overflow stream and recover the coarser portion, we can use water as an aid in the classification. So what we can do here is we have a feed material containing different sizes. I'll just use my pointer here. So for example, in sedimentation classifiers, we have a feed material. Pulp density is typically what we use to quantify the percent solid in it. So we could say, for example, 50% solids coming in. And what we normally use is water going against the feed. So feed comes from the top, water goes against the flow of the feed. And in this case, as we discussed last week, if particles can resist the upward flow of water or the water going against them, they can settle through that, okay? And they can be collected as a coarse product. But if particles are too small or too light, the water will push them up and they will go to the next classifier. And in the next classifier, in this case, for example, we could target medium or medium-sized particles. And what we'll do is, in comparison to the first cyclone or cylinder here, we will reduce the velocity by which we introduce the water. So here, it's high velocity coming up, so only the courses will settle through here. As you reduce the flow rate or as you reduce the velocity of the water going up, some of the medium particles now will get a chance to settle and be collected as a medium product. And then as you go to the next one, so the fine or the lightest particles will be carried over to the next cyclone. And in this one, again, we reduce the velocity of water a bit further, allow finer product to be collected, okay, in this portion here. And the ultra fine particles or the slimes will be collected in the overflow stream. So essentially you could have a number of these cylinders one after the other and classify particles based on their size. You can also use density if that is what you have in your operation. So if particles are the same size, but they have different densities, then the same principle can be used. So in this case, the densest ones will fall first, will be collected in the coarse product, and then you have medium and so on. So as you can see here, the cylinder gets bigger and bigger, obviously, because every time you go to the next cylinder, you introduce more water. Okay, so you have to allow for that additional water being introduced, and therefore the capacity of the cylinder needs to be a bit bigger. So we can do that and do what we call a sedimentation, where particles can be classified into different size fractions. Okay, so this is one option. But also if you go to different mining operations, you also tend to find simple classifiers where you have a very big tank and you basically feed the particles from the top, such as this one here. And obviously, because particles are solids, they're denser than water. With time, they should sink to the bottom of that tank. And in this case, the shape of the tank can look like a cone, where you have a narrow at the discharge end and the cone is wider at the feed end, which means as slurry comes down, obviously with water, denser particles, larger particles will settle, and that will build up over time. As the solid accumulate and build up over time, you will have at least two zones. The first zone or the bottom zone should be mainly made from solids, so it's a sediment, and then you have an overflow area or an overflow region. And therefore, as you continuously feed, what should happen is obviously the material should go somewhere. So eventually, as soon as you reach a certain height, the sediment will push and exit through the discharge. And as you feed continuously, obviously you will displace some of the top layer here. The top layer here usually contains fine material, fine particles, and that will overflow. So you would have two streams again. So you will have a sedimented high percent solid at the bottom and an overflow containing mainly water and probably some fine particles with it as well. So this can be operated in different ways. For example, you could use it purely for just wastewater treatment, okay? Or you could use it for other applications. In mineral processing, we use, for example, thickening is a process where we go from a low percent solid pulp to a high percent solid pulp using thickening as one way. So, and the way the thickness work is simply by allowing particles to settle and then recovered as a discharge at the bottom of a cylinder. And if you have very fine particles, which obviously take longer to settle, we can also add flocculants, and flocculants obviously aid with the aggregation of particles together. And as particles aggregate, they become larger and they settle faster. So we, for example, thickeners work in the same way. Probably thickening or solid liquid separation is something we'll talk about in your next course in process eng 2. So don't worry too much about thickening and all those operations at this stage. And so that's one example of how a typical classifier may work. Another type of classifiers are the ones that use some kind of mechanical means to remove the solids that settle at the bottom. Okay, so in this case, for example, this picture on the right shows a spiral classifier, okay, where you have a feed coming from the top and you have a region here where you allow solid particles to settle. And obviously as the solid particles settle, they will accumulate at the bottom here. And once you have that accumulation of solid, you can use some mechanical means to remove from the bottom. So you could, for example, use a rake, which constantly drags the solid up, or a spiral, again, which rotates gently, picking up particles and pushing them upwards. So eventually, your solids will make their way up and discharge it, while whatever is in the overflow would be very fine particles or slimes with water, okay, and that would be collected as an overflow discharge. Okay, so again, based on whatever mechanism you use for removal of the solids, it can be a spiral or a rake classifier. Other type of classifiers, as I said, probably hydrocyclones are more common in many operations, and they don't actually use any mechanical means to remove the solid. They're purely based on the properties of the solids that we're feeding into this equipment. And based on the size of the solids we're feeding or based on the density, we can also just track the motion of the particles, separate the solids that are coarser from the ones that are finer by just using cyclones. And I will talk about hydrocyclones in the next slides. Okay, so how does a hydrocyclone work? If you guys are not familiar, so a hydrocyclone is basically like a conical shaped vessel, okay, where your feed is introduced in a particular motion. So when you introduce the feed of a cyclone, you actually introduce it from the top here, and it follows what we call a tangential motion. So feed is introduced, makes a bit of a spiral motion inside the cyclone. Okay, so we're purposely introducing the feed in such a way that it forms a spiral motion inside the cyclone, and these are operated at very high pressures. So the internal pressure inside the cyclone is very high. And what should happen is as particles do this motion, circular motion, if particles are coarse, they will have a net centrifugal force that pushes them to the wall of the cyclone. Okay, so coarse particles will tend to aggregate somewhere around here, around the wall of the cyclone, while fine particles will have a drag force that's influencing the motion inside the cyclone. And drag force usually acts inwards. So in this case, you have solids that are coarse or dense going to the wall, solid particles that are smaller or lighter being dragged to the center, So eventually, because you are also feeding this continuously, you would have solids exiting in the underflow stream here. So underflow usually contains coarse particles that have been dragged to the wall of the cyclone. And the fine particles, which have been dragged to the center of the cyclone, will eventually exit through what we call the vortex finder, which is pretty much an overflow containing fines and large amount of water. Okay, so that's essentially how a cyclone works, by just moving the particles inside the cyclone in a circular motion, coarser ones attaining a centrifugal force, going to the wall of the cyclone, and smaller ones dragged to the center of the cyclone, eventually exiting the cyclone as overflow stream. So what happens inside the cyclone, or what are the forces, as I mentioned, are, as I said, this is how particles are introduced. Essentially, they do a circular motion in the cyclone, and coarse particles tend to go outwards, okay? And fine particles tend to go inwards. And the corresponding forces can be dependent on the size of the particles, of course, the density of the particles and the density of the fluid that you are operating in, and of course, on the tangential velocity as well, which is usually a higher number in comparison. And in terms of fine particles, the drag force again is dependent on particle size. But essentially, because the centrifugal force is highly dependent on the size, larger particles will eventually possess a significant centrifugal force, and therefore that's why they will be drawn to the wall of the cyclone. Okay, so as I say, large particles, dense particles have a higher centrifugal force compared to the drag force, and therefore they will go to the cyclone wall and exit through the spigot. That is what we call the spigot, the underflow area. And small particles or light particles will tend to have a higher drag force, which then will be dragged to the low pressure zone, to the middle of the cyclone, and they join the air core. So the air core is simply because the cyclone is open, there's a potential for air to pass through this, and eventually that's where they exit the cyclone as overflow stream. So as you can see, this is a very simple operation relatively. So as long as you have reasonable difference in particle size or particle density, that should be operated in a reasonable efficiency. If you're very keen to know what goes on inside the cyclone, so this is just one cyclone. We don't have compartments actually inside it. Okay, so there's no compartment or anything. It's just purely based on hydrodynamics inside that cyclone. So obviously, as I said, we feed it from the top. So region A, I don't know if you guys can see this clearly, but hopefully if you can see, region A is where the feed is introduced and you have unclassified material. So it's basically the feed is just entering the cyclone. You haven't done anything, no force have started to act on it just yet. So region A is unclassified and it is adjacent to the cyclone wall, okay? And basically the roof of the cyclone and so on. And this box here is what we call the vortex finder. So when we make up the cyclone, we have a vortex finder which is protruding, which is going a little bit into the cyclone. Okay, so this is a solid tube, if you like, okay, where we're going to allow fine particles to pass through. I think maybe I'll show you that previous. Yeah, so can be this one here, okay, going a little bit deeper into the cyclone, or maybe this one here, okay? If you look at here, so the vortex finder actually goes a little bit into the cyclone, okay? So that's what this one is showing. Okay, so feed goes in initially unclassified, but as it goes down, obviously because you're constantly feeding, particles are constantly coming, so whatever entered the cyclone will be pushed down and more feed will come in. Okay, so this is a continuously operating process. So you have, as I said now, as particles go into the middle of the cyclone, forces will act on it, and the solids that are larger will be dragged to the wall of the cyclone, and eventually they will make their way down the cyclone and exit here. So region B here is coarse material that has been classified. Okay, and in the same way, we have the fine materials which have been dragged to the center of the cyclone, now exiting through the overflow, and therefore region C here is fine material that has been classified. So it is actually in this region D, you actually have classification happening, where particles have been introduced, particles that are coarse will be dragged to the wall, the fine ones will be dragged to the center. So that's where true classification actually happens. Okay, so this is basically what happens. And obviously at some point you have a situation where now you have coarse particles here, fine particles here. So you're talking about a size, a cut size, where if particles are smaller than that size, they will go to the overflow. If particles are coarser than that size, will go to the underflow, right? So that cut size is the critical factor that will influence the performance of a classifier. So in this case, when I say cut size, let's say you have particles that are varying in size from 1 micron to 250 micron. Okay, so this is a very wide size range, and you have a cut size maybe happening at 100 micron. So what you're saying is particles smaller than 100 micron will go to the overflow. Particles that are coarser than 100 micron will go to the coarse portion, which is the underflow, and therefore you have the cut size happening at 100 micron. Okay, so always when we try to estimate the performance of this classifier, we just want to know of all the fine particles we had in the feed, what fraction actually went to the fine. Of all coarse particles we had in the feed, what fraction actually went to the coarse portion. That's what we're assessing when we work out the performance of a classifier. Okay, we'll talk about cut size and classifier performance a bit later on when I do the example, so no stress there. Okay, so I mentioned to you that when we introduce the feed into a cyclone, it's usually in a tangential motion. So we give it a swirly or spiral motion as it goes into the cyclone. And there can be slightly different designs. Okay, so for example, in the involute design, the open area is a little bit wide. Okay, so these broken red dots actually show you the regions where solid feed can enter the cyclone. On the other hand, in the tangential motion, the tangential inlet is only this region where we allow particles to pass into the cyclone or to enter the cyclone. You can have maybe a bit of both. Okay, so the partial involute is taking a bit of the design of the tangential and that of the involute, and you can have that in this manner as well. So these ones probably depend, which one you choose will depend on your requirements and what you're trying to achieve. But the tangential motion is by far the most dominant, but there are some benefits and limitations of each of those designs. For example, in the involute design, okay, usually works well, it's compact because you have a very wide opening area where the feed can enter the cyclone. You can operate them at higher capacity as well. Okay, so can be operated at higher capacity. And again, as particles enter the cyclone, they will be dispersed. So erosion of the cyclone is not very high, okay, unless you are, of course, overloading, or if you have abrasive particles, of course, erosion will still occur. But because particles are released in a wide area into the cyclone, usually erosion of the interior of the cyclone is minimized, okay? What are the other limitations for inlet, involute inlet? Probably slightly more complicated to fabricate. It's not impossible, but more sophisticated than the tangential inlet. And because particles enter in a wide area, okay, the opening is wider, you will have significant pressure drop, obviously, okay, as particles go into the cyclone. And with pressure drop, usually what happens is the forces that act on the particles will vary. For example, if you have very high pressure, you would even have the ability for fine particles to attain a centrifugal force and be drawn to the wall of the cyclone. If the pressure drop inside the cyclone is very high, which means you have a lower pressure inside the cyclone, in this case, coarse particles may go to the overflow and report with the fine portion. Okay, so those are some of the limitations that you need to consider when there is significant pressure drop inside the cyclone. Okay, in contrary, if you have a tangential motion, okay, the opening here is very minimal, so there's less pressure drop, okay, and if there's less pressure drop inside the cyclone, fine particles can be classified properly. So that's one advantage of a tangential motion. And of course, lower capacities in comparison to the involved. And as I mentioned, they're very common in many places. People just use tangential inlets as their cyclone feed. And that's mainly because they're lower in design and in cost as well, and that can be classified or taken as one of the advantages of tangential inlet. Probably one major limitation is because feed is going in a narrow gap, in a narrow opening, what happens usually is they have a reduced capacity, okay, in comparison to the involute inlet where particles can enter in a wide area where you can operate your cyclone at a reasonably high capacity. Okay, so because I'm probably going to talk a little bit like this, maybe it's good to stop and see if you guys have a question so far. Okay, do you guys understand, or at least do you have an idea of how a cyclone works, or is it too confusing? So let me know if there are any questions, at least in terms of how hydrocyclone works. If it's all clear, then we can continue. Okay. So if everyone is on the same page, then that's good. So when we operate a cyclone, there are certain things that we need to be mindful of. And that's typically the way the underflow is discharged. Okay, when you operate, especially the lab scale cyclones, when you operate them, you can actually see how the underflow or the solids exit the cyclone. And usually the shape you're looking for there is a hollow cone shape. Okay, if you have a discharge that looks like this, then you're probably operating the cyclone reasonably well. Okay, so it's actually saying that you are achieving a reasonable percent solid and you are allowing air core or air to enter the cyclone reasonably well, and your efficiency should be very good. But in some cases, you have situations where the cyclone underflow sprays too much, or you have the underflow looking a little bit like a rope. Okay, so if you have spraying kind of shape like this one, a very wide cone, then what this one is saying is your cyclone is actually discharging lots of water. Okay, so yes, we expect solids to exit through the underflow, but in addition to the solids, you are also discharging lots of water. So we expect the water to go with the fines to the overflow, but if there's too much water being discharged as the underflow, basically you have reduced the density of the underflow, and with water you usually carry fine particles as well, and therefore instead of the fine particles going to the overflow, they're actually going with the solids that are coarser. So in this case, you would significantly reduce the performance or the efficiency of the cyclone. So spraying usually means water is discharging in that end, and with that, fine particles are discharged. And we don't want fine particles to discharge. We expect only the coarse particles to discharge at the discharge end. And therefore here, you should have a very low underflow density as a result of the excess water exiting there as well. So the other option or the other possibility is the discharge looks like this one, like a rope. So discharge has difficulty exiting the cyclone, and this actually tells you that this is a very high percent solid discharge exiting. So you're not allowing any air into the cyclone. So you have a lot of problems. If this is the case, one, because you're not discharging enough solids to start with, you should be operating at a very low capacity. And also you should be discharging only a limited amount of water. And that would usually mean that you will be operating at a very reduced efficiency as well. So roping is a very common problem. So our cyclones usually operate maybe percent solids. You would expect around the exit at the underflow is maybe 75%, 70%, somewhere there. If it's too high, if it's in the 90%, then you have a problem with roping. And with roping, efficiency decreases, capacity decreases, and therefore you'll be running into problem very quickly. Okay, so most of the cyclone models that we use to predict performance of a cyclone can also predict if roping can happen during operation or not, based on whatever variables and operating conditions you select as well. So if you happen to see cyclones in operation, it's common to have a number of them stacked together. So some cyclones could be about 12 in one operation. You could even have 18 or even 24 cyclones working together in one operation. So in this case, for example, you have one cyclone here, another one here, another one here. So feed goes into the cyclone, overflow to the top, and underflow here. So basically what you have is you have a feed coming and split into 12 cyclones or 18 cyclone or whatever number of cyclone you have. And the overflows from each of those cyclones are collected, and the underflows from each of those cyclones are collected, and you will have two streams exiting the system. So you have overflows from all the cyclones going in one direction, and underflow from all cyclones going in another direction. So obviously this kind of setup will make it difficult if, for example, something is stuck in one of the cyclones. Okay, could be a wood or could be anything, could be plastic. Sometimes you have metals and everything that make their way to the cyclone and they just block. Usually it's not easy to work out what's going on, and you don't know if all your cyclones are operating at the expected rate or not. So when those happens, usually you might need to do regular maintenance to see all the cyclones are operated at a reasonable rate without any issues. But regardless, it's common to find a number of these in one setup and can be operated reasonably well. So as you can see, they're simple to build. All you need is just a pump and a cone. And you basically pump your material into this cone. And as long as you have the required pressure, you should have overflow and underflow streams. And they can be very small or they can be very large. So this actually depends on the size of your plant, obviously, but they can be made really small if you want, or they can be made large. So you could have, say, cyclones operating at 500 tons per hour, or you could have minimum ones that can operate at 1 tons per hour or even smaller. So depending on the operation, the size can be easily manipulated. They're easy to build, and therefore they have very low cost associated with them. And because you have very high pressure inside the cyclone, you can actually mount them in any direction. If you want to incline them, you can put them, you can erect them horizontally, you can have them even upside down. Okay, so the underflow can be up and the overflow can be at the bottom. because of the high pressure inside them. They could be operated in any position. And of course, sometimes we have a thick pulp coming in, and even that can be classified because there is a very high shear force inside the cyclone. Okay, so of course, if you want to operate them, you have to use a pump. So maybe pumps can be considered as moving parts. They can be considered as a risk to operate. Okay, but also because you need to generate a very high pressure inside the cyclone, it could mean that you probably may pay a lot in terms of energy because you're pumping the slurry at a very high rate. Okay, so energy consumption can be one of the issues associated with them. And if you are looking at the wrong feed material, efficiency can be very poor as well. Okay, so sometimes that may mean if you have a poor efficiency as a result of operational parameters, then your cyclone may not give you whatever you're expecting to get from it as well. Okay, for example, as I say, could be imprecise separation. And of course, 2 micron is very small in mineral processing, but if you wanted to go even beyond that, if you want to classify particles below 2 micron, then they're not going to work, simply because of the requirement for very high internal pressure to be able to classify fine particles. As soon as you hit somewhere around 2 micron or lower, they're not going to be effective. But generally speaking, we don't actually need to go that fine in many mineral processing operations. Even when we do desliming, where we want to get rid of fine particles that are somewhere around 10 micron or more, cyclones are commonly used. So in those operations, when we do desliming, the main purpose is to get rid of very fine particles. And when I say fine particles, I'm talking about typically 10 to 20 micron particles. Even then, cyclones can be used, but obviously there will be a limit if you want to go below 2 microns in particle size. Okay. And of course, because again, you're operating at high pressure, internal erosion could be very high. So your cyclone inside of the cyclone can be deteriorated, can be eroded very quickly. And for that, people use liners. So you can put rubber liners and so on, which you can replace every now and then. And that can be used as a way of reducing cost associated with them. Okay, so what could be the cause for inefficient operation of a cyclone? So as we say, we have 2 streams generated from a cyclone. So you have overflow fines and underflow coarse. Those are the 2 streams we generate. But it's possible, because it's just one single unit, the cyclone is one single unit, it's possible for the fines to report to the coarse portion and the coarse portion to go to the fines. Okay, the only way to control that is by simply the forces inside the cyclones are what govern the operation of that and what should go to what. So for example, if you have dense particles that are really small, just because they're very small doesn't necessarily mean they go to the overflow or the fine fraction. Especially when you have dense particles, even if they are small in size, they could still go with the coarse particles. Okay, that's simply based on the fact that they may develop enough centrifugal force, and rather than going with the fine, because they're denser, they will probably go with the coarse particles. So that can be, for example, one reason for inefficiency of a hydrocyclone. Or if you're feeding very coarse particles, again, very coarse particles, they may not respond to anything that's happening inside the cyclone. Okay. In this case, again, coarse particles could randomly go to the fine or to the coarse portion, and they may not be affected by the forces or the hydrodynamics inside the cyclone. Okay, so these are, I'm talking about excessively large particles, which you might introduce. And again, that can be another reason for inefficiency inside a cyclone. So how do you measure that? How do you measure inefficiency? I think I mentioned about this slide last week. So we could develop a performance curve or a partition curve where we track particles which are reporting to the coarse portion or the oversize, as compared to the one in the feed. And as I said, we can develop a partition curve that looks like this one to plot and see how efficient a cyclone is. So I talked about causes for inefficiency in a cyclone, and I mentioned about this curve last week as well. So in this case, for example, here, if it was a very efficient classification, this curve here should be here at the bottom here. But instead, we have about 25% of particles shortcutting into the coarse fractions. So what I'm saying is basically these particles, if this was my cut size, I expect all these particles smaller than somewhere around here. All these particles shouldn't go to the underflow or shouldn't go to the coarse portion. So all this should be somewhere here. But instead, I have an error because fine particles are going to the coarse fraction. That's what this one is saying, basically. Fine fractions going to the coarse. And here, as you can see, if all the coarse went to the underflow, this should be 100%. Okay, so this blue line here should be here, but it's saying not all the coarse are actually going. So the curve is saying not all the coarse particles are going to the coarse fraction. Some actually are going to the fine fraction. That's why I have this less than 100. So again, this one here tells me that actually coarse particles are going into the fine fraction. Okay, this portion here is telling me fine particles are going into the coarse fraction. This is saying coarse are going to the fine fraction. So these are what we call short circuiting of fines to the underflow, basically this one here, and short circuiting of coarse particles with the feed into the overflow. And that's why this is not quite 100%. Okay, so that's less than 100% because some of these coarse particles went to the overflow or the fine portion. So these are how we can calculate. So obviously, the higher this is, the poor classifier performance is. As you bring this one down, okay, if the curve goes close to 0 around here and close to 100 around here, then you have a reasonably efficient classifier. Okay, so I also showed you this formula, how we can calculate imperfection. Basically, it tells you whether a classifier is efficient enough or not. So to give you a rough idea of how we interpret that equation there, this one here. Okay, so probably simplified using this one here. So in this case, the partition curve can be constructed by working out recovery of particles in the underflow to that of the feed. So for any given size. So in this case, so let's say 200 micron. What we're saying here is 200 micron particles in the underflow or in the coarse fraction in comparison to 200 micron particles that I initially had in the feed. So this is 200 micron particles that went to the coarse versus 200 micron particles that I had in the feed. So I just mentioned 200, but it could be any size, okay? Could be 500 micron that went to the coarse versus 500 micron particles in the feed, or 50 micron particles that went to the coarse versus 50 micron particles in the feed. So this is how we define these two, and we can work out the recovery for each particle size, okay, that we had in our feed material. Okay, so for example, let's say you have 16 ton per hour material of a certain size in the feed. So when you say certain size, so maybe you started with 100 ton. Okay, so the feed to the cyclone is 100 ton. Of the 100 ton that's going into the cyclone, maybe 16 ton per hour is 250 micron particle size. Okay, so if that's the case, then let's say of that 16 ton per hour particular size fraction, 12 ton per hour went to the underflow, which means the remaining 4 ton per hour actually went to the overflow. So when we write percentage reporting to the underflow, it is 12 divided by what we initially had in the feed, which is 16. So this actually tells you recovery should be somewhere around 75%. So basically what I'm saying here is, although I had 16 ton per hour, a certain size fraction in the feed, only 12 ton per hour went to the coarse, which means 4 ton per hour went to the fine portion. So whatever reported to the coarse portion is 75%. So what about the remaining 25%? For that size fraction, 25% must have gone to the fine portion or the overflow. Okay. So again, that 25% went to the overflow or the fine portion because it wasn't really classified. It wasn't impacted by the forces inside the cyclone. So if I wanted to obtain a rough idea of actually how much of it is recovered in the underflow because of the actual classification happening, then I need to calculate that from whatever fraction of water that has gone to the underflow. So basically in this case, we need to correct this value here by considering possibly some of the particles could go with water into the overflow and with water into the underflow as well. And to correct that, we use this equation here. So again, these are the ones that I have collected, say total 250 micron particles in the underflow, total 250 micron particles in the feed. But I know some of whatever I collected here may be because of true classification, but some could be because of water carrying them with it as well. And therefore, that's why we need to take into account the fraction of water that was in the feed. And in this case, for example, if say about 25% of feed water reports to the underflow, with that 25% feed water, you actually have some coarse particles being carried as well, some fine particles being carried as well. So 25% of water material here actually says that maybe actually even out of the 12 that I have collected here, 12 tons per hour, not all of the 20 to 12 ton per hour was because of classification, but some of it is because of the water that's carrying the particles, and that is about 4 ton per hour for just the water. So in this case, what I'm saying is, yes, about 8 ton per hour of that size fraction was collected because of classification, but about 25% or about 4 ton per hour was actually carried with water. And therefore, if I wanted to know the result of a true classification, that's only about 67%. Okay. So how about the rest? The rest was actually because of the fact that water carries some of the solid particles with it. So if I wanted to maximize operation of a hydrocyclone, or if I want to improve efficiency, my water in the underflow stream should be minimized. Okay. That's why I said earlier, if you have too much water coming in the underflow, if it's spraying too much, okay, as a spray discharge, then it's saying the underflow density is very low. It's saying there's a lot of water exiting. With water, you have not only coarse particles, but fine particles exiting as well. And therefore, the efficiency should be significantly reduced. Okay, so that's what this one is implying. But obviously, this is just for one size fraction, but we can do the same for various size fractions. So if I give you a feed, that feed doesn't necessarily have one size. It probably has a very wide size. Okay, so you just mill something, for example, you just had a ball mill operating, producing particles that are very wide in size, from say 5 micron, 10, 20, 50 micron, 100 micron, 250 micron. So you have a spectrum of particle sizes produced as a result of grinding. So I can't just take 100 micron and do my assessment on that, I have to take the whole spectrum of particles that have been produced by grinding. And then I will take that and do my classification assessment as well, based on a spectrum of particles that has been produced after grinding. And therefore, you need to do partial coefficient curve, addressing all the particle sizes under consideration. Okay, so in this case, if now you take into account the fraction of water exceeding with the underflow, you have what we call a corrected performance curve. Now the R here simply takes into account the fraction of feed water that is being recovered in the underflow. So as I said, the more this is, the lower your efficiency of a hydrocyclone performance is. So maybe after correcting it, really what should happen is this should drop. Okay, and corrected performance curve, for example, here is shown in the pink line here. And this is corrected because this only takes into account not particles short circuiting as a result of water, but particles that are being recovered only as a result of classification. And the x-axis here, typically for particle size, that's what you will use. But if you're classifying particles based on their density, light and heavy, then you can use specific gravity here. But as I said, typically we use particle size on the x-axis to work out performance curves. Another thing you could do is plot a reduced performance curve. So I said corrected curve is mainly accounting for water. And with the water, we have solid particles being carried as well. That reduces performance. So that's why we correct that. But sometimes maybe you have 3, 4 cyclones, and maybe you run different operations for different particle sizes, or even different minerals or different ores for different cyclones. So maybe it's not really easy to compare one cyclone with one set of data with another cyclone with another set of data and another cyclone with maybe even another mineral sample. Okay. So to limit the variation in operation and the variation in sample or nature of sample and so on, you could actually use what we call reduced performance curve. And this is purely used to compare one cyclone from the other and see how each of those cyclones operate and what the performance of each of them is. And to do that, we just divide the reduced or the corrected performance curve on the x-axis by D50. So D50 is simply a size here, okay, at 50% partition coefficient. So this is the size. And we take D50, divide the x-axis by D50, and we normalize it. So in this case, now the x-axis becomes dimensionless. Okay, instead of having in micron or specific gravity, if I divide the x-axis by, say, D50 size, then this becomes dimensionless. Okay, so now it's not really dependent on particle size or specific gravity, just the curve simply compares different classifiers or different hydrocyclones with one another. And if you did that, you have reduced performance curve where the sizes are now divided by the D50, or D50 is our cut size or our separation size. Okay. And you could have something like this. So then I run, different tests, different experiments using different samples. Maybe I compare performance of 3, 4 different cyclones, and I plot my performance curve. And in this case, I would compare reduced performance curve of the 3 cyclones, cyclone A, cyclone B, and cyclone C of different samples, as I said. And maybe I get something like this. And then I look at them and I say, okay, this cyclone C here is terrible because it doesn't give a good curve. Cyclone B is okay, still very poor, okay? But cyclone A is maybe acceptable, okay? Because it's getting closer to the theoretical performance curve or the perfect separation. So by comparing just the curve, which has been normalized, I could just predict which cyclone is more effective or which cyclone is efficient. And this is useful, especially when you're designing cyclone. Okay, so people design cyclone with different lengths, with different dimensions. They try them on different samples, and they can take a data and plot different performance curves for them. And they can actually compare and see. And obviously, these curves are very useful when we design cyclones and when we want to assess how cyclones are performed. So in this case, for example, curve A looks like a reasonable sharp separation, highly efficient, okay? And you normally get these ones when you operate, for example, hydrocyclones that are not really too dense, or if the slurry is of moderate density, then you would get something like this. If you feed very thick pulp or very dilute pulp, then you run into problems. So typically, maybe you would feed your cyclone at about maybe 50 to 60% solids. Okay, if you go to say 20% or low percent solid, then it's probably very dilute. If you go beyond say 70%, then you're already feeding very thick pulp to the cyclone, then your performance should drop in relation to whatever you are feeding. Okay, so just to give you a rough idea. And of course, a number of other examples for other classifiers as well. And again, in comparison, B and C here don't look sharp separation at all. Maybe that's because you are overloading the cyclones. Maybe you are using it for a closed circuit where overgrinding is a problem. You're continuously feeding it with very fine particles and so on. And maybe the percent solids you're feeding it is very high, and this would then result in very poor performance. So you need to look at the curve and see what you need to change. So typically what people do to optimize a cyclone performance is you look at two things. Either you would change the feed water composition, okay, so you reduce or increase feed water going into the cyclone and try to optimize that. Or the other thing you do is you play with the pressure. So pressure can be increased or decreased. As you increase or decrease the internal pressure, you would then have the opportunity to either drag finer particles to the wall and reduce your cut size. With that, you may also improve your efficiency of hydrocyclone or a classifier performance. So it all depends on those factors. Usually we don't play with modifying the cyclone itself. Yes, you can change the dimensions of the underflow. You can change the dimension of the overflow or the vortex finder. You can change the inlet diameter. All those factors affect the cut size. I'll talk about that a little bit later on in probably the last slide. But in this case, usually you have the cyclone already designed and on site. You can play with operating variables like pressure and water to first fix and see if you can optimize the cyclone. Okay, so probably I don't talk too much about models, but people have been trying to develop lots of hydrocyclone models in the past. And usually what we do is we take a data from a small lab scale cyclone. Maybe in this case also you might have a simulated pulp density. Usually they work with low percent solids. And they take that data and they somehow try to develop numerical models and try to assess the performance of a cyclone based on those models. So the issue with this kind of practice is usually the fact that you're already working with a very small cyclone. In this case, I'm talking about very tiny cyclones. And it's not realistic. It's not really applicable to what happens in the actual plants. And whatever model you come up with usually may not be accurate. It may not actually reflect what happens in a real size or a big size plant. But regardless, you can see how changing pressure affects cut size, for example, or changing pressure changes the hydrodynamics inside the cyclone and so on. And people use these models. For example, I hope you guys are familiar with, say, CFD, computer fluid dynamics, and people try to work out the various hydrodynamics inside a cyclone by changing some variables, and typically they then use that for developing different design hydrocyclones and so on. There are actually a couple that are commonly used in hydrocyclone design. The first one is the Plith hydrocyclone model, as you can see here, and usually applied, as I said, for larger diameter hydrocyclone with relatively high pulp density, and these are probably close to what we actually see in the proper industry. And in this case, the D50 is predicted using this guy's model based on the diameter of the cyclone, the inlet diameter, the overflow or vortex finder's diameter, and the underflow diameter. And H here is simply the height of your cyclone. So we measure it from the vortex finder to the apex, and that gives you the height of the cyclone. And V represents, I think V is here, and represents the volume percent in the feed, and Q represents the feed rate in the slurry. And of course, you can take into account the solid and liquid density as well. So in this case, particles are what you're feeding. You can take the average density of those particles. And if you're operating in water, you take L as the density of water. And some cyclones use dense media rather than water. So you don't have to use water as a media. You can actually use other media. For example, you can make a media from very fine particles of ferrosilicon or magnetite, or you can even use hydrocarbons, which are not really popular at this stage because they're toxic. But you can prepare a dense media, and particles can be suspended in a dense media, and hydrocyclones can be operated on that kind of phenomena as well. So again, if that's the case, then you take the density of your media as L. But regardless, you can predict the D50 based on set of conditions. So again, if you want to design something and you want to see how cyclone diameter affects D50, then you fix everything else and you just change the cyclone diameter. If you want to see how the underflow or apex diameter affects the D50, you fix everything else and you vary the underflow diameter and try to see how the D50 varies with that. So you can actually use this and try to work to find a suitable cyclone model, or you can just use these models to predict how a cyclone behaves. If I change pressure, if I change this, or if I change that, what happens? So in this case, for example, by just playing with the volumetric flow rate, which again is dependent on the pressure, the inlet pressure that is, you can then relate the two and you can try to optimize and see what the effect of, say, changing the pressure is on cyclone performance. And usually when we use, again, I don't know if you guys take a unit that deals with plant design and optimization, but if you do, you probably would find some of these models in software. So we use, for example, softwares like JK here, or even you can use Syscad and so on to optimize some of these models and predict cyclone performances. But obviously those are probably for another course. I don't know which course that's going to be necessarily in, but you could find some of these models anyway incorporated into hydrocyclone model. For example, one of the options that the software gives you could be Plith's model. You could have another model by Mueller. You could have other models that could apply based on what you're looking at in that particular software package. So again, another similar one that you can use for predicting hydrocyclone performance and for predicting model parameters and so on is the Mueller and Joule cyclone model. And for this one again, you could have a custom built cyclone geometry with known dimensions. So cyclone diameter, inlet diameter, vortex finder diameter, underflow diameter, those can be fixed and you could have those predetermined already. And you can then predict D50 from the slurry volume you are pumping into the cyclone, which you can measure. So you can measure your slurry. It is fed, say, at 100 meter cube per hour or whatever. And based on that, you can predict. So the cyclone diameter is already known. You can predict the D50 values from measuring the volumetric slurry flow rate and so on as well. Okay, so as I said, where do you use the cyclone models? You can use them for design and optimization purposes to predict performance. And sometimes maybe you're just curious. So you say, what happens actually if I change this? Okay, so you can run simulated models and see for those hypothetical changes that you're trying to implement in the plan, you can somehow try to roughly work out what may happen. So you could say, for example, so maybe we want to increase the capacity of the plant. We want to go bigger. Let's buy bigger cyclones. Obviously, with bigger cyclones, you're changing the dimensions of the cyclone. So cyclone diameter changes, inlet diameter changes, everything changes. So for those, you can then predict what will be the consequence of just the size of the cyclone on the cut size. Okay, can I then still separate my particles into fine and coarse? Okay, or do I need to pump too much? So in this case, when you increase the cyclone diameter, your pressure requirement will increase. So you need to pump more, and we need to increase pressure inside the cyclone more. With that comes energy cost. So you can work scenarios which then will help you whether that's a sustainable thing to do or not. Or sometimes you may say, instead of having 10 cyclones, can I go have 24 smaller ones instead? Okay, so what are the trade-offs? Okay, on capacity, on performance, on cut size, on efficiency, you can work those scenarios as well. Okay, and even before you have a plant on site, you can predict how many cyclones you would require, for example, for a typical capacity of a plant. Okay, so these are some of the things maybe you can keep an eye on. So as I said earlier, if you're keen to optimize performance of a cyclone, maybe you can start with changing the density of the feed. Okay, so easily, for example, if I increase density of the feed, which means I'm putting more solids per volume, and in this case, I should easily increase the pulp viscosity. Again, we talked about when you have very high percent solids, you're talking about hindered settling condition where particles will start to interact with one another, okay? And because of that, particles are not free to move inside the cyclone, and you should reduce the sharpness of separation, okay? And with sharpness of separation, what happens is coarse particles, instead of going to the underflow, may go to the overflow, which means you increase the cut size, okay? So again, that can be one issue. And again, as I increase pulp density, I may reduce the pressure drop, so there's less pressure inside the cyclone, or the change in pressure from the inlet to whatever is inside the cyclone will then affect whether I can separate coarse particles and draw them to the wall of the cyclone and exit through the underflow, or whether those coarse particles actually report to the overflow stream as well. So these are some of the things that can happen, even theoretically speaking, before you touch anything. You can see changing pulp density will have consequences on a number of factors, okay? And the same is true, for example, for inlet diameter. If I increase inlet diameter into the cyclone, now I am actually making the inlet wider, which means as particles enter, the velocity will drop, okay? So as particles enter, velocity will drop, and with that, your pressure inside the cyclone will drop. Okay, if I introduce them at higher velocity, particles will still have high pressure inside the cyclone. But if the velocity reduces all of a sudden very quickly, then there will be a very small pressure inside the cyclone because of that significant pressure drop from initial to whatever is in the cyclone. And again, that will have an issue again. Instead of drawing more coarse to the wall, coarse particles will exit through the discharge to the overflow and join the fine particles. And the same is true if, for example, I increase vortex finder. I told you vortex finder is where the fine particles exit from the cyclone. If I make that wide, then I'm allowing more particles to go through the vortex finder. Okay, so in this case, not just fine particles exit, but coarse particles will also exit through the vortex finder. I increase the cut size. Okay, so this can already be predicted before we even do any experiments or any test because of whatever happened. And obviously, I'm assuming all the other factors are not changing. I'm just changing the vortex finder's diameter. Everything else is kept constant. And then I'm seeing the effect of changing the vortex finder. Okay. And if you change spidule diameter, which is the discharge end, you allow more water to exit. Obviously, more water exits means you would have less percent solids in the underflow. And with that, I allow more fines. With more fines exiting the underflow, I would reduce the cut size significantly as well. Okay. Of course, these are some of the consequences you can predict. And in the same way for pressure increase, if I increase pressure, then you would have higher flow rate. You would have the opportunity to drag more particles to the wall, even the finer ones to the wall of the cyclone. And these finer ones will discharge through the underflow. Again, I reduce the cut size. So again, these can be predicted. And this is what you will probably have to play with. So when you operate the cyclone, you say, maybe when you initially started, you plant, maybe 120 micron was the cut size. So as the plant progresses from month to month, year to year, obviously that cut size may not always stay there. And if cut size drops quickly or increases quickly, these are some of the things you can change to adjust and optimize the performance of a cyclone. Okay, so to summarize, we could look into free and hinder settling conditions. Each of them can have an impact on the performance of a classifier, and you need to understand what's going on, okay, and how these situations affect the performance of any classifier. Okay, so whatever condition you have, you could still work in free settling condition, you could work in hinder settling condition. The main point here is for whatever condition you are working at, you need to pick a condition that suits the operation and also the equipment that you are working with. And in terms of classifier performance, I mentioned to you how we measure performance, but I'll probably do a couple of examples to help you understand, okay, how we construct partition curve and so on a simulated data. But before I go there, I'll probably pause a little bit and see if you guys have a question. Any questions so far?
Hello, teacher.
Yes, yes.
During the hydrocyclone method,
Yeah.
during the hydrocyclone classification method,
Yeah.
does the impurity or purity of water affect the process?
Okay, very good question. So, okay, I think you're finished, yeah?
Yes.
Okay, so when we say purity of water, we're actually talking about a number of factors. So it could be just ions in the water. So it's common. I'm going to pause, I think mute your side because there's some feedback coming. Okay, yeah, so when we say purity of water, it could be just ions like calcium, magnesium, sodium. Some water actually have very high ionic strengths. If we're talking about ions like those, it has very low impact. The water, whatever water you add, shouldn't have any impact on the performance of hydrocyclone. But some water has a large proportion of suspended solids in it. Okay, so we call that TDS. And if the TDS is really high, and and the particles you're trying to separate are really fine. So for example, if I'm working at separation of about 10, 15 micron particles, and I'm adding a very impure water into the system, then I expect that to have an issue. Because as we said, even particles as small as 2 microns could be classified. Okay, so if you have particles in water that are larger than 2 microns, they will definitely have an impact on the classifier, because those particles in the water will also have either a drag force or a centrifugal force, depending on where you are operating, depending on the cut size and so on. And then it will have some kind of impact. But generally speaking, if it's normal process water or water that you are using for a typical mineral processing operation, usually water quality shouldn't have significant effect on hydrocyclone performance, okay? Unless, as I said, you have a very impure water with very large suspended solid in it. Probably some other operations like flotation can be very sensitive to water quality, because some ions can interact with the particles, they can change surface chemistry, and we know flotation, for example, is surface chemistry dependent. Okay, so that can have significant impact. Or water quality may have an impact on leaching, because again, with leaching, we're talking about interaction of chemicals with the particles. And if you have some chemicals in water, those could have detrimental effects. But if you ask me, typically whatever water you use in mineral processing operation, as long as you purify that, in hydrocyclones, those shouldn't be a significant problem. Okay, sorry, I muted you, so I'm going to unmute again. Oh, I can't unmute, so Elias, maybe you can unmute and see if anyone else has a question.
Okay, I do have a question.
Yeah.
I do have questions on hydrocyclone.
Yeah.
In this procedure, as you said, the final particles go to the overflow in the courser, and heavier denser particles to the underflow. But in case of screening,
yep,
does it have an opposite with that of the hydrocyclone? But when we screen the materials,
yep,
the coarser particles go to the overflow, and
yep,
the smaller and finer particles to the underflow. So is it an opposite relation with that of the hydrocyclone?
Okay, very good question. So maybe it's good to be careful on terminologies. Okay, I'm going to mute because there's some feedback. Okay, so it is only terminology. So when we look at the screening, whatever that passes through the screen is what we call undersize. Okay, so undersize means smaller fraction. Oversize means coarse fraction for screening. Okay, so for classification, I think the term I was using was overflow and underflow. So overflow means the fine portion, as I said, but overflow means for screening, it is undersize. Okay, so for site classification, we call it overflow, but when I say overflow, it just means undersize or fine fraction. For the coarse portion, we call that obviously the coarse fraction or the underflow. And in this case, the underflow means the oversize. So I think as long as you use the terminologies properly, it shouldn't be a problem. So as I said, if you say oversized, undersize for screening, undersize means overflow, okay? Oversize for screening means oversize. We're not saying overflow for screening, we're saying oversize. And oversize for a screen is underflow for a cyclone, okay? I don't know if it makes sense to you guys, but it's more of a terminology. I think if you go to the lecture last week, I think I put a slide there explaining once you do screening or classification, the coarse fraction can be called sand, or it can be called oversize, or it can be called underflow. And the fine portion can be called slime, or it can be called overflow, or it can be called undersize. So it's just a terminology. I know it's a bit confusing, I think, but just use the right terminologies, but they should mean the same thing regardless. Okay, but yeah, typically for screen, we say oversize, undersize. For classification, we say overflow, underflow, but you need to use the right terminologies in the correct manner. Okay, again, I can't hear because I'm muted, but if you guys have any other question, let me know. Any other question, or you want me to explain that? Okay. Okay, so ሌላ ጥያቄ ከሌለ ኦር መጠየቅ ትችላላችሁ ይሄን ኤክሰርሳይዝ ስንሰራ። አይ ሆፕ ይታያችኋል ይሄኛው ስላይድ። ስለዚህ አንድ ሁለት ኤግዛምፕል አለ። ይሄ ጀስት ሲሙሌትድ ዳታ ነው ለቲፒካል ክላሲፊኬሽን። ለምሳሌ የሚያደርግ ሰው ኦቨርፍሎ እና አንደርፍሎ ኮሌክት ያደርጋል። ከዛ በኋላ ኦቨርፍሎ እና አንደርፍሎውን አሳይ ማድረግ እንችላለን። ሳይዝ ፓርቲክል ሳይዝ ዲስትሪቢዩሽን ልንሰራለት እንችላለን። ስለዚህ ይሄ ቴብል የሚያሳየው እንደዛ አይነት ኦፕሬሽን ነው። ከሃይድሮሳይክሎን የተገኘ ዳታ ነው። ስለዚህ የምንፈልገው ምንድን ነው? ፓርቲሽን ኮኤፊሽንት ኮንስትራክት ለማድረግ የሚያስፈልገንን ዳታ ኮሌክት ማድረግ ነው። እስቲ መጀመሪያ እዩትና then we'll see how we go. I think አሳይመንታችሁ ላይ አንድ ጥያቄ አለ ከዚህ ጋር ሪሌትድ የሆነ። ስለዚህ ይሄን ከሰራችሁት ሞስት ላይክሊ ያኛው አሳይመንት ላይ ያለው ጥያቄ ስትሬት ፎርወርድ ነው የሚሆነው። Okay, so I think 100 ton per hour assume ማድረግ ትችላላችሁ ለኦፕሬሽኑ። ስለዚህ ፊድ ከሆነ ይሄኛው ኦቨርፍሎ አለ እዚህ ጋር፣ አንደርፍሎ አለ እዚህ ጋር። ስለዚህ ይሄ ፋይን ፖርሽን ነው ቅድም እንዳልኳችሁ በዚህ ጋር ኤክሲት ማድረግ ያለበት። ኮርስ ፖርሽኑ በዚህ ጋር ነው ኤክሲት የሚያደርገው። ኦኬ ሶ ጀስት ሲምፕል ኦፕሬሽን። ስለዚህ እነዚህ የሚያሳዩት ምንድን ነው? ቴብል ላይ የተሰጣችሁ አንደርፍሎ ኮሌክት ይደረጋል። አይ ዶንት ኖ 100 ቶን ፐር አወር ከሆነ ኦፕሬት የሚያደርገው የተወሰነ ፖርሽን ሳምፕል አድርገን እሱን ሳይዝ ዲስትሪቢዩሽን አናሊሲስ መስራት እንችላለን ማለት ነው ላው ላይ። ስለዚህ ማስ ፐርሰንት ኦፍ አንደርፍሎ የሚለው የተሰጠው እዚህ ጋር ምንድን ነው? እሱ ከአንደርፍሎ ሳምፕል ተደርጎ ፓርቲክል ሳይዝ ዲስትሪቢዩሽን ተሰራበት። ከዛ ይሄ ነው ዲስትሪቢዩሽኑ። ኦኬ ኦቨርፍሎ ሳምፕል ተደረገ፣ ከዛ ፓርቲክል ሳይዝ ዲስትሪቢዩሽን ተሰራበት፣ ዴን ዲስትሪቢዩሽኑ ይሄንን ይመስላል። ስለዚህ የተጠቀምነው ሜሽ ኦር የተጠቀምነው ሲቭ እነዚህ ናቸው። ኦኬ ስለዚህ 100 ቶን ፐር አወር ከሆነ የጀመርንበት ፊዱ 100 ቶን ፐር አወር ከሆነ በተሰጣችሁ ኢንፎርሜሽን አንደርፍሎ ስንት ቶን ፐር አወር ነው፣ ኦቨርፍሎ ስንት ቶን ፐር አወር ነው የሚሆነው። ጀስት ምንም ነገር ሳታደርጉ እሱን ካልኩሌት ማድረግ ትችላላችሁ። መጀመሪያ እንዴት ነው ማድረግ የምትችሉት? ስፕሊት ተሰጥቷችኋል እዚህ ጋር አንደርፍሎ ስፕሊት 0.87 ነው አዝ ኤ ፍራክሽን ወይም ደግሞ 87%። አንደርፍሎ ስፕሊት ተሰጥቷችኋል which means ከመቶ ቶን ፐር አወር ከሆነ ከመቶ ቶን ፐር አወር 87 ቶን ፐር አወር አንደርፍሎ ጋር መሄድ አለበት። ስለዚህ የቀረው 13ቱ ኦቨርፍሎ ጋር ይሄዳል ማለት ነው። ኦኬ ስለዚህ this is just a basic framework ምንም ነገር ከማድረጋችሁ በፊት። ስለዚህ ይሄን ዲስትሪቢዩሽን ከሰጣችሁ ይሄ በፐርሰንት ነው የተገለጸው። እዚህኛው ላይ ሪቴን የተደረገው ይሄ ነው፣ እዚህ ላይ ሪቴን የተደረገው ይሄ ነው ተብሎ ነው የሰጣችሁ። ከፐርሰንት ይልቅ ማሱን ከፈለጋችሁ ለምሳሌ በዚህ ሳይዝ ሬንጅ 2.3% ነው ያለው። በዚህ ሳይዝ ሬንጅ ያለው ወደ አንደርፍሎ የሄደው ግን ከፐርሰንት ይልቅ አክቹዋል ማሱን ከፈለጋችሁ በ87 ብታባዙት ማሱን ማግኘት ትችላላችሁ። ሶ 2.3% ታይምስ 87 ቶን ፐር አወር አክቹዋል ማስ ማግኘት ትችላላችሁ እዚህ ጋር። ኦኬ ስለዚህ ለሁሉም ማስ ማግኘት ትችላላችሁ በ87 በማባዛት። ለኦቨርፍሎ ፐርሰንት ነው የተሰጣችሁ። እዚህ ሳይዝ ፍራክሽን ውስጥ ያለው ለምሳሌ በዚህ ሳይዝ ፍራክሽን ውስጥ ያለው 0.4% ነው። ከ13ቱ 0.4%ቱ ምንድን ነው በማስ ብለን ኤክስፕረስ ማድረግ እንችላለን ይሄንን። ስለዚህ እነዚህንም እንደዛ ኤክስፕረስ ማድረግ እንችላለን። ስለዚህ ከፐርሰንት ማስ ፐርሰንት ይልቅ አክቹዋል ማስስ ቴብል ልናወጣ እንችላለን እዚህ ጋር ማስ ኦፍ አንደርፍሎ ኢን ኢች ሳይዝ ፍራክሽን፣ ማስ ኦፍ ኦቨርፍሎ ኢን ኢች ሳይዝ ፍራክሽን። እሱን ካገኘን then ፊዱን ለማግኘት we just add underflow with overflow. Okay, we get the feed. ፓርቲሽን ኮኤፊሽንት ከርቭ ለመስራት ምን ያስፈልጋል ብያችኋለሁ? አንደርፍሎ ቱ ዘ ፊድ ነው ፕሎት የምናደርገው ዳታውን ለማግኘት። ስለዚህ ኦልሬዲ አንደርፍሎ ካገኛችሁ እዚህ ጋር ማስ ኦፍ አንደርፍሎ ፎር ኢች ሳይዝ ፍራክሽን፣ ፊዱን ደግሞ ይሄን ይሄን እንደምራችሁ ካገኛችሁት ፎር ኢች ሳይዝ ፍራክሽን። ስለዚህ ፓርቲሽን ኮኤፊሽንቱ መስራት ትችላላችሁ ማለት ነው። ኦኬ ኦኬ ስለዚህ ይሄ የሚለው 87% ነው። ስለዚህ አንደርፍሎ 87 ቶን ፐር አወር ነው። ኦቨርፍሎ 13 ቶን ፐር አወር ነው። ስለዚህ እንዳልኳችሁ እዚህ ጋር ወደ አንደርፍሎ የሚሄደው 87 ከሆነ ይሄንን ኮለም በ87 ማባዛት ነው። ስለዚህ እዚህ ጋር ቶታሉ እንዲሆን የምትፈልጉት ስንት ነው? ተደምሮ 87 ነው ቶን ፐር አወር። ይሄ ደግሞ ተደምሮ እንዲሆን የምትፈልጉት 13 ቶን ፐር አወር ነው። ኦኬ ግን 17 እና ማን ነው 87 እና 13 ቶታል ናቸው። ቶታል ማስ ከ100 ቶን ፐር አወር ብንነሳ የምናገኘው ማስ ናቸው። ወደ አንደርፍሎ የሄደውና ወደ ኦቨርፍሎ የሄደው። ኦኬ ስለዚህ 2.3 by 87 እዚህ ጋር የሆነ ቫልዩ አገኙ። 9.3 by 87 እዚህ ጋር የሆነ ቫልዩ አገኙ። ለዚህም እንደዛው 0.4 by 13 4.2 by 13 እያልን ቫልዩ ማግኘት እንችላለን። ያን ካረግን ምንድነው የምናገኘው? ማስ of this size fraction ለምሳሌ in the underflow ማስ እናገኝለታለን። ኦር እዚህ ጋር ብንመጣ ለምሳሌ mass of this size fraction in the underflow ቫልዩ እናገኝለታለን። mass of this size fraction in the overflow ቫልዩ እናገኝለታለን። ስለዚህ ያደርግን ያለነው ምንድነው? ለእያንዳንዱ ሳይዝ ፍራክሽን ምን ያህሉ ነው ወደ አንደርፍሎ የሄደው፣ ምን ያህሉ ነው ወደ ኦቨርፍሎ የሄደው የሚለውን ነው የምናገኝለት። ኦኬ ለእያንዳንዱ ሳይዝ ፍራክሽን ስል ለዚህ ሳይዝ ፍራክሽን ለእያንዳንዳቸው ሳይዝ ፍራክሽን ይሄ እንዴት ነው የሚወሰነው? ይሄ እንደ የኦፕሬሽኑ ነው። አንዳንዱ ፓርቲክል ሳይዙ ሲጀምር ለምሳሌ 500 ከሆነ ኮርስ ፓርቲክል የሚባለው ከዚህ በላይ ያለው ማድረግ there is no point። ምክንያቱም ምንም እንደሌለ ካወቅን ይሄን አልሲቭ መምረጥ የለብንም ማለት ነው የግድ። ኦኬ አንዳንድ ኦፕሬሽን ደግሞ ሜቢ ፋይን የሌለው ኦፕሬሽን ሊሆን ይችላል። ስለዚህ ለምሳሌ ከ150 በታች ምንም ከሌለ እነዚህን ሜሽ ሳይዝስ መጠቀም አይጠበቅብንም ማለት ነው። ስለዚህ የምንሰራው ፓርቲክል ሳይዝ ዲስትሪቢዩሽን የሚወሰነው ራፍሊ ባለን የፓርቲክል ዲስትሪቢዩሽን ፓርቲክል ሳይዝ ዲስትሪቢዩሽን። ኦኬ ሶ ሪጋርድለስ ይሄንን ኮምፕሊት አድርጉት። ስለዚህ ይሄንን ሮ አይ ሚን ይሄን ኮለም በ87 አባዙት፣ ይሄንን በ13 አባዙት። you should have something like this. Okay ስለዚህ 2.3 by 87 ሁለት ነው። 9.3% by 87 ስለዚህ እነዚህ ፐርሰንት ናቸው። ስለዚህ ይሄን እናገኛለን። ስለዚህ ምን እያልን ነው? 100 ቶን ፐር አወር እንደመነሻ ብንወስድ ወደ አንደርፍሎ ከሄደው ፓርቲክል ውስጥ ለምሳሌ 5.5 ቶን ፐር አወሩ ቢሎንግ የሚያደርገው እዚህ ሳይዝ ውስጥ ነው እያልን ነው። ኦኬ በተመሳሳይ ደግሞ 2.4 ቶን ፐር አወር ወደ ኦቨርፍሎ ሄዷል ለዚህ ሳይዝ ፍራክሽን። ኦኬ ሶ ዊ ዱ ዘ ሴም። ለምሳሌ ይሄን ሳይዝ ፍራክሽን ብንወስድ እና ኦፕሬሽኑ 100 ቶን ፐር አወር ቢሆን ከዛ ውስጥ 0.3 ቶን ፐር አወር ቢሎንግ የሚያደርገው አንደርፍሎ የሄደው እዚህ ሳይዝ ፍራክሽን ውስጥ ያለው ነው። በተመሳሳይ ደግሞ ይሄ ሳይዝ ፍራክሽን በኦቨርፍሎ የሄደው 0.7 ቶን ፐር አወር ነው። ስለዚህ ያወራን ያለ ነው ኢንዲቪጁዋል ሳይዝ ፍራክሽንስ going to underflow and overflow. Okay, I hope it makes sense. ስለዚህ ፊዱን ስፕሊት ነው የምናደርገው ወደ ሁለት ወደ ኦቨርፍሎ እና አንደርፍሎ። ስለዚህ ፊዱን ማግኘት ከፈለግን መደመር እንችላለን ሁለቱን። እንዴት ነው የምንደምራቸው? ይሄንን እንወስዳለን ከዚህ ጋር፣ ይሄንን ኮለም እንወስዳለን ከዚህ ጋር፣ ይሄን ኮለም እንወስዳለን ከዚህ ጋር። ሁለቱን ብንደምር ፊዱን እናገኛለን እዚህ ጋር። ኦኬ ስለዚህ ሪኮንስቲቲዩትድ ፊድ የምንለው አንደርፍሎ እና ኦቨርፍሎውን ደምረን የምናገኝ ነው ማለት ነው። again for each size fraction. okay so each size fraction under question. አንዳንዴ ይሄንን ሚን መውሰድ እንችላለን። ለምሳሌ ይሄ የሚያሳየው ምንድነው 850 እና 1180 ማይክሮ መካከል ያለ ሳይዝ ፍራክሽን ነው ይሄ የሚያሳየው። ስለዚህ the smallest one is 850, the largest particle is 1180 እያልን ነው ማለት ነው። ግን የሁለቱን አቨሬጅ ብንወስድ አቨሬጅ ፓርቲክል ሳይዝ እናገኛለን። ስለዚህ እሱን መጠቀም እንችላለን። እሱን ቫልዩ ከዚህ እስከዚህ የሚለውን ትተን ሚን ሳይዝ ፍራክሽን መጠቀም እንችላለን። ስለዚህ ሚኑ የሁለቱን ደምረን አቨሬጅ በመውሰድ የምናገኘው ነው። ኦኬ ሪጋርድለስ። ስለዚህ አሁን ፓርቲሽን ኮኤፊሽንቱን ለማግኘት ምንድን ነው የምናደርገው? አንደርፍሎ ዲቫይድ ባይ ፊድ ነው የምንለው። ስለዚህ አንደርፍሎ ይሄ ነው፣ ፊድ ይሄ ነው። ስለዚህ አንደርፍሎ ባይ ፊድ ወደ ፐርሰንት ቀይረ ነው ፓርቲሽን ኮኤፊሽንቱን እናገኛለን ማለት ነው። ስለዚህ ለላባችሁ የምሰጣችሁ ዳታ እንደዚህ አይነት ነው። የሃይድሮሳይክሎን ኦፕሬት ተደረገ አት ቱ ፕሬሸርስ፣ ሁለት ፕሬሸር ነው ኮምፔር የምናደርገው። ለሁለቱም ፕሬሸር ፓርቲክል ሳይዝ ዲስትሪቢዩሽን ለኦቨርፍሎ ለአንደርፍሎ ይሰጣችኋል። ከዛ በኋላ ከርቡን ኮንስትራክት ማድረግ እና ከት ሳይዙን ኦር ዲ50ን ካልኩሌት ማድረግ እንደዚህ አይነት ነገር ነው ኤክሰርሳይዝ የምታደርጉት። ኦኬ ስለዚህ አንደኛው ጥያቄ ፓርቲሽን ኮኤፊሽንት ካልኩሌት አድርጉ ነው የሚለው፣ እሱን ሰርታችኋል። ኦር እንደዚህ ነው የሚሰራው እሱ። ሁለተኛው ጥያቄ ስፒጆት ሳይዝ ስፒጆት እንዳልኳችሁ ይሄ ነው። ስፒጆት ሳይዙን ብትጨምሩት ምንድን ነው ኢፌክቱ ነው። ዲ50 ወይም ከት ሳይዙ ላይ ምን አይነት ኢፌክት ሊኖረው ይችላል ነው። ስለዚህ እንዳልኳችሁ ይሄን ብትጨምሩት በፊዱ ከፊዱ የሚመጣው ወተር አብሮ ኤክሲት ያደርጋል ከአንደርፍሎ ጋር። ብዙ ወተር ኤክሲት ባደረገ ቁጥር ደግሞ በዚህ ፋይን ፓርቲክልስ አብረው ኤክሲት ያደርጋሉ። ኦኬ ስለዚህ ፋይን ፓርቲክልስ ኤክሲት ካደረጉ ከት ሳይዙ ይቀንሳል ማለት ነው። ኦኬ ሶ you could say the cut size decreases as you increase the spigel diameter. Okay. Okay, does that make sense guys? ጥያቄ ካላችሁ እዚህ ጋር ጠይቁ።
In the case of such kind of exercises, the underflow speeds are given, but if the underflow speeds are not given, how can we calculate or find?
So if the underflow and overflow information is not given,
the underflow speeds, if the underflow speed is not given,
yeah,
the overflow and underflow information may be given.
Yeah.
If the underflow speed is not given, how can you calculate this to?
Okay, so I only partly heard what you said, but if you have overflow and feed, you can still work on this problem because you can always calculate the underflow from the feed and overflow. Okay, if you have just the underflow without any other information, then you can't do much with it. So you have to have either feed and overflow or feed and underflow or you should have underflow and overflow. So we need to do particle size distribution on at least one of the streams, either the overflow or the underflow. Okay.
I do have a question.
Yep. Okay.
Having this information, partition coefficient, how can we draw the partition curve?
Uh-huh.
To use to draw the partition curve,
Yep.
Which particle size? I mean, which particle size we use, because we don't have here the mean particle size are not given. So how
Yep.
can we draw the partition curve?
Okay, very good. So, as I said, you can calculate mean. So much feedback coming, so I'm going to mute. I'm muting because I'm hearing myself again and again, so I have to mute. Okay, yep. So if you have the particle size distribution given there, so in this example here, for example, the first one is 1250 and 1180. So basically what it says is we used sieves of 1250 and 1880, then 850, then 600, then 425, and so on. So to calculate the mean, what we need to do is sum, for example, this one with this one, okay? And then take the average, so that will give us a mean. So 1250 plus 1180 divided by 2, we can get a mean here. Okay, so it doesn't have to be given. This is something you can calculate. And here we say 1180 plus 850 divided by 2. We have a value here. So this is for the mean. Mean. And again, 850 plus 600, I get mean values here. So I can do the same for all these. And of course, once I do that, I have partition coefficient E for each of them. So then I have corresponding values of E here. And then when I plot, what I'm plotting is mean particle size on the x-axis and partition coefficient on the y-axis. Okay, so as long as you have the sieves and the size is given here, you should be able to calculate the mean by just taking the average. Okay, so average of those two, plus and minus average of the two is just add them, divide by 2, and that should be the mean for that particular size. Okay, so for this particular size, it is the average of those two. For this one, it's the average of those two. And of course, this goes all the way to the corresponding value of E. And again here, 425, 300, average of those two, and the corresponding value of E. And I have X and Y, so I can plot the partition curve. Okay. And from the partition curve, you can calculate the cut size, you can calculate the imperfection, okay, which we're going to do in the next example.
Okay, I have two questions regarding to these problems.
Yeah.
The first question is, how can you calculate or estimate first if the mass split of the feed is not given? In that segment, is not given. So without this information, how can you calculate it?
Yeah. So I think he asked the next one as well, and I will mute after that.
And the second question is the three streams, which is the feed stream and the feed stream, underflow and overflow streams. How can you, the mass flow rates of those three streams can determine from the given information?
Okay, thank you. So I'm muting, as I said, because I can't hear when I talk. I just hear myself, so I have to mute. So the split is actually determined from the mass flow rates. I think your questions are very related. So the 87% is actually calculated from flow rates. So I have feed coming, okay, at 100 ton per hour. So this is operational variable. So if that's the capacity at which I am operating, I can take that as my feed flow rate. And then you can take timed samples for the underflow and overflow. Okay, so in this case, you can capture the overflow stream for 10 seconds. You don't need more than that. And you can capture the underflow for 10 seconds. And from that, you can either determine the volumetric flow rate. Okay, volumetric flow rate, I just say I captured maybe 20 liters in 10 seconds. So I have volume with time. So that will be your volumetric flow rate. And you do the same for the overflow, volumetric flow rate. Or you can actually calculate mass flow rate. And to do mass flow rate, you need to filter the water out and dry the sample. And once the water has been removed, so we actually do that. We take a sample, do filtration with a filter press or something like that, and then we dry the sample and we can determine the mass. Okay, maybe I took again example for 10 seconds, 20 liters, let's say. I filtered that out. I have a mass for the underflow and I have a mass for the overflow. Then I can determine the mass flow rate as well. So typically you can sample timed samples and determine mass flow rates. Once I know mass flow rates, of course, I can determine the mass split. I know if 80% is going to the underflow, either in volume or in mass. Okay. And then I know what goes into the overflow. I think once you know overflow and underflow, you don't have to determine the feed. But if you want to determine the feed, you can always add the two. But that's how we determine. So the split is dependent on mass flow rates, basically. Okay, and that's obtained by taking time samples.
So another question?
Yep.
Okay, in the cyclone, the assumption is the feed is equal to underflow and the overflow. But what if there is a loss? How can we manage that?
Okay, so the way a cyclone works is this is basically closed. So whatever goes to the cyclone goes in a pipe. So basically, you are pumping the pulp through a pipe. Okay, unless there is, of course, a leakage inside the cyclone. If there is a leakage inside the cyclone, of course, it's not going to work properly. Because as I said, there is a very high pressure inside the cyclone. If you have crack inside the cyclone, you should be able to visually see any crack on the cyclone, and you shouldn't operate that cyclone. But regardless, here we don't have any material transported from one place to another. So the overflow is captured in a pipe, the underflow is captured in a pipe. As long as you sample that properly, there shouldn't be any loss, essentially, right? So that's why we don't assume any potential losses in underflow or overflow. So basically whatever you add up between the overflow and underflow should give you the feed. Okay. So otherwise, if there is I don't know, I'm not familiar with any other way of operating a cyclone where there is a potential loss, but there shouldn't be any loss practically. As I said, if there is leakage, then it is already a hazard. You shouldn't operate a cyclone. But as long as you sample the underflow and overflow properly, it shouldn't be any issue at all. And it's probably more of a sampling issue rather than any sample loss. Okay. So that's why if I'm given overflow and underflow samples for a cyclone, I just assume that should add up to the feed. Okay, unless someone tells me otherwise.
As you said, during the hydrocyclone classification.
Yep.
During the hydrocyclone classification, the type of water, I mean the total dissolved substance, will affect on the classification, because the particle in water have centrifugal and drag force, so this may affect on the classification. So what will be the limit of the total dissolved solute in water just for a better classification during hydrocyclone? I mean, for example, for drinking, the total dissolved substance may be greater than it may be 10 TDS, it may be 30, it may be 300. So there is different types of water. So what TDS amount will be preferable just for a better classification of such a kind technique?
Yeah. So okay. So good question. So the TDS obviously depends on how fine the suspended solids are. So I also mentioned dense medium cyclone. Okay, we need to be a bit clear, I think, on this one. So what matters the most is not just having high TDS. Here in Australia, we have waters that have, say, 200,000 TDS, waters that are very saline.
Your sound is not audible.
Okay, sorry. I think you can hear me now. Okay, so as I was saying, here, can you hear me?
አሁን ይሰማል።
Okay. So I don't know what part you heard, but anyway, what I was saying here in Australia, we have very high TDS water. Whatever we dig from the ground is even very high in TDS. And as I say, the problem is not high TDS or low TDS. The issue in cyclone, especially, is if you have coarse particles suspended in the water. You could have low TDS water, but coarse particles in it. On the other hand, you would have high TDS water, but very fine particles in it. So if you ask me the difference between those two, I would say the one that's low TDS, but coarse particles will be a problem. But even if my TDS is 2,000 or 200,000, and if it's very high, if it's actually fine particles, say less than 1 micron particles, I wouldn't worry too much about it.
Because what makes the problem is actually if the solids in the water are coarse and they actually interfere with whatever other fine particles I'm trying to classify, it becomes a problem. For example, maybe I'm trying to classify 5 micron particles, but already the water contains 8 micron particles. That is a problem, even if it's a low TDS. So the limit is not on TDS, it's more on particles that may present in the water that are coarse. As I say, you could have low TDS, you could have 200,000 TDS, still you could operate a cyclone of air. Okay, so that's probably one thing we need to address. And the other issue is I mentioned dense medium separation. And for dense medium separation, we actually use a dense media that's made from particles. And in this case, we suspend 75 micron particles, 50 micron particles to make up the media itself. Okay. Already this is a dense media containing particles. So your water shouldn't be worse than something like this. But when we do like this, when we use medium, dense medium separation, we actually try to separate coarse particles from one another. There's no point in preparing a dense media that is made from 75 micron particles, but at the same time you want to separate 20 micron particles from one another. It doesn't work like that. So you should also use dense medium containing 75 micron particles, 50 micron particles suspended in it. But what we're trying to separate would be, say, particles that are 1 millimeter in size or 5 millimeters in size from one another. Okay, so I use dense medium with lots of fine suspended particles in it. But what I'm trying to separate is coarse particles from one another in millimeter size. Okay. As I said earlier, the issue with water quality becomes a problem only when I have coarse particles in the water, but what I'm trying to separate is actually even finer particles from one another. That is a problem. So otherwise, TDS alone shouldn't be problematic, especially if it is what we're trying to separate from one another is coarse particles, say in millimeter size range, then I wouldn't even worry about water quality. But if you're asking me, oh, okay, I have some water with solids in it, but what I want to classify are 10 micron particles, then I say, okay, you have a problem here because the particles can interfere. The particles in water can interfere with classification. Okay? So it depends on what we're looking for. Okay, so as I say, cyclones can be used for sliming. If you do cyclones for the sliming, what you're doing is getting rid of 10 micron particles. But cyclones can be used for beneficiation as well, based on density. If you do that, you are probably looking at 5 millimeter particles, 1 millimeter particles, 10 millimeter particles, very coarse particles. So those are different things and depends on what operation you're using it for. But in both cases, it is separating fine from coarse. At the end of the day, in both desliming operations and beneficiation operations, all we're trying to do is separate coarse from fine. But obviously, the level of coarse in one operation is totally different from the level of coarse and fine in another operation. Okay, any other question?
We have already finished our question.
So let's do the next example. Okay, so very similar to the previous one, except in this case we use two-stage classification. And I will also show you how we plot the curve actually. I didn't show you how we plot the curve in the previous example, but I can show you how we plot the curve in this. Okay, so we have exactly the same problem as the previous one. So in this case, feed coming in the first cyclone, we have overflow and underflow. But the difference is once we have the underflow in this one, the underflow from the first cyclone becomes the feed to the second cyclone. And we split that into overflow and underflow. Okay? So what is given in this table are samples and the corresponding particle size distribution. For the whole stage, overflow and underflow represent this one and this one. So we take samples, we do particle size distribution on them to determine those. And for stage 2, this is the feed. We take samples from the underflow and overflow. We determine particle size distribution for also basically related problems. And so you're being given particle size distribution for overflows and underflows. So basically what this one says is, this is if you wanted to write it in the same way as the previous one, like this, plus and minus, you can do that. So this one is plus 650, or 6.25, or in microns, that would be 6,250. So that's given in millimeters. You can convert it into one. And this range here is minus 6.25. Okay. 5 plus 3.35. And this one here, if you want, means minus 3.35 plus 170, and so on. So you can write them like this one. So this one would be minus 170 and plus 120. Okay, so the table doesn't show that, but that's what you should understand when you look at the table like this. If I give you like this. So if I ask you to again work the mean arithmetically, or the mean size, you could just say, for example, for this one here, it is 6.25 plus 3.35 divided by 2. You do the mean here, and you can do the mean. Anyway, so once you have that, for your PVD for the first cycle, the split is 69.7. Okay, so basically here, if you start with 100 tons per hour, 69.7 goes to the underflow. The remaining goes to the overflow. So we can actually calculate the actual masses in ton per hour, okay, instead of the percent in ton per hour. So we can actually do that. So don't worry about stage 2 for now. For stage 1, it comes in, splitting overflow and underflow, and in this case, the particle size distribution for each is given. Okay, so follow the same, give us a lot of information that you can reach with this one. That's basically the same concept. So you can take the mean by adding this, divide by 2, you get that. Add these two, divide by 2, you get that, and so on. So that's the mean. And for cyclone 1, overflow and underflow are given. And we've been given the split here is 39 for 69.6 for 63.7. For the remaining out of 100, we go to the overflow at 30.3. So multiply this by 30.3 to get this, and multiply column 5 by 69.7, we should get this one. So the first thing we can do is calculate column 4 and column 6 by simply multiplying by 30.3 and 69.6. Of course, these ones are expressed in percent. So 3.43 means 3.343%, which is 3.43 by 100. Okay. So this is taking an example here. So if we have 0.04 size fraction that belongs to this one, and multiply this by 30.3, you should get this value. And in the same way, 4.51 divided by 69. Okay. And basically, you can complete all the other ones, all the other missing ones. Those are the same example. Okay. So we do mass of overflow, mass of underflow, the feed, 110 by adding this column here is this column here. We should get when it comes to so that would be overflow plus underflow in mass, and that should add up to 100 tons if we're assuming 100 tons. Okay. So obviously we're using 100 tons per hour to simplify, but your actual operation would be 500 tons per hour. If that's the case, then we use the exact same capacity. If it's something else, we use the same ratio. So I don't think that's a problem. Okay, so I think we can focus on just this one. If everyone can get these values, and for the field, they get these values, and for they can see why it is 1, or in this case, 100%, is either fractional or percentage. You can use either. Go from 0 to 1 or go from 0 to 100, depending on whether you take percent or fraction. I'm okay with either way. So everyone tries that and let me know if that values, if it doesn't make sense or if you're not getting the same numbers, let me know and we can work on it. And so if we did those, I think this is how we should complete the table. As I said, the P here can be expressed in percent out of 100. So in that case, 1 would remain 100. Okay. So whether you use 100 or 1, I'm okay. Doesn't really make a difference as long as you're doing the right thing. Okay. So if you can see how we complete this table, then once I do this, now we can go with the next one. So if you look at the cyclone information given, so the split to the underflow was 69.7% for the first cyclone and 82.6% for the second cyclone, which means of whatever comes here, 82% splits the underflow. Okay, so I already know what comes here. What comes here from the previous example. If I assume 100 tons per hour operation, is I know 69.7 tons per hour comes to the underflow, which is now the feed for the second cyclone. Of that, of 69.7, 82% of 69.7 comes here. So basically, we can work out 82.6% of 69.7 to get whatever squeeze to the underflow. And once you know that, you can always calculate 69.7 minus whatever this one is should give you. Okay, so that's what we do for the second cyclone. And in that case, second cyclone underflow split is 57.5 and overflow split is 12.2. Okay. And everything else is exactly the same. Okay, so we've been given information about overflow, underflow size distributions, So the difference is you can either use underflow from cyclone 1, okay, which is now feed for cyclone 2. You can do that, or I just add column 5 with column 7, and that should give me the feed into the second cyclone, which should also be similar to this one. Okay. So to get the feed for second cyclone, feed for the second cyclone can be obtained by just taking the underflow from the first, or by adding overflow and underflow for the second cyclone. Either way, should be very similar to this one. And now I have underflow mass, divide that by feed, I get my partition coefficient. Okay. So once I have partition coefficient, so that can be plotted on the y-axis. Mean size can be plotted on the x-axis, and that will give me my partition. Okay. So partition coefficient on the x, sorry, on the y, mean size on the x-axis, and that will be cyclone 1 curve that I'm showing here. That. Cyclone 2 is shown in blue, and you can actually get a combined classification from cyclone 1 and cyclone 2 as well. And to get the combined, all you have to do is add underflow from the second cyclone and divide that with the feed for the first cyclone. So what I mean is, if you take underflow divided by feed, okay, so underflow for second cyclone divided by feed of the first cyclone, will give me the overall or the combined cycle performance. Because what happened was feed came here classified, and then take the underflow classified. So these are the overflows, total overflows from the two, and this is my underflow. So basically, if we assume this as one unit, so we have feed, so overflow, underflow. So to get the combined, all we have to do is take underflow from the second, divide by feed to the first, which will take the combined, which should look like the one shown here. Okay. So the question then was to calculate imperfection. And as I said, imperfection is dependent on D75, which is here for each of them. So D75 for cyclone 1 is here. D75 for cyclone 2 is here. And D50 for cyclone 1 is here. And D50 for cyclone 2 is here. And D75 for each of them. For the first one, I think you need to extrapolate a little bit to get the D25, because you're going to have data points one way or the so you can consider extrapolating the curve, which may not be ideal, but I think this is situation okay. And you get these values here. So for cyclone 1, imperfection is about 1.2. Cyclone 2 is imperfection about 0.5. So comparing the two, you can say second cyclone is a lot more efficient. And you can think of why that might be the case. It is because already the feed to second cyclone, is classified. So you have classified it, whatever flows to the second cyclone, the underflow here is actually a lot more controlled in size. Okay, because overflow has taken some of the files in it. So we're feeding a very narrow particle size range into the second cyclone. That's why it's a lot more efficient compared to the first cyclone. And the combined would be somewhere between the first cyclone and the second cyclone. So the second cyclone is very efficient first cyclone is not so efficient, combining this relative. So efficiency is again a relative term. So if you get values of less than 0.2, usually that represents an ineffective or inefficient classifier. Somewhere between 0.3 to 0.5 is good. Somewhere over 0.7 is actually bad classifier. And again, that number or that range can range from places to places, from operations to operations, even from what kind of cyclone you're using to another one. But generally speaking, less than 0.2 imperfection shows a very good classifier. Okay, so this is just to comment on why efficiency of the second one is better than the first one and why the combined is lower than the first one. So I think those are around the fact that second cyclone should be efficient because of the feed, and the feed has been already classified in the first cyclone, so that's why it is more efficient. Okay, so you should get a bit of exercise from the assignment and also from the lab work, hopefully, and you should have a bit of understanding on how these things work. Okay. But feel free to ask questions. በተሰጠኝ ሲለበስ መሰረት አይ ቲንክ አብዛኛውን ነገር ከቨር አድርጌያለሁ። የሆነ ስፔሲፊክ ቶፒክ ካላችሁ የሆነ ዲስከስ ማድረግ ትፈልጉ
ይሰማል?
ጥያቄ ያላችሁ
ይቆራረጣል።
ኦኬ አይ ቲንክ ጥያቄ ያላችሁ ወይም በዚህ ጀምሯል ዛሬ ስለሆነ ክላስ ነው። All good? ምንም አይሰማኝም። ስለዚህ
ጥያቄ የለንም። ጥያቄ የለም፣ ግን ምናልባት ዛሬ ነው ክላስ የሚያልቀው። ስለ ቀጣይ ሳምንት አሁን ለኛ ቢያንስ አሁን ካየናቸው እንትኖች ውስጥ ከሁሉም ሪቪው ነው ቶታል ሪቪው ብታደርግ ሁሉም
ሪቪው ማድረግ እንችላለን። ስለዚህ
ከሁሉም ቻፕተሮች ላይ በደንብ እንትን ያለ ቢያንስ 2 ሰዓት እንትን የሚል ሰመሪ ነገር ሪቫይዝ ብታደርጉ ቀጣይ ሳምንት ላይ እና ደግሞ ላቡን ሰኞ ለመስራት አስበናል። ስፔሻሊ ሳምፕሊንግን ሲቭ አናላይሲስ እና ጂኦክራሸር እና ቦል ሚድም ሰኞ ለመስራት አስበናል። ኦኬ ምናልባት ለዚህ የሚያስፈልግ ወይ እንትን ካለ ለማኑዋል ነገር ካለ እንትን ሼር ብታደርጉ እስከ ሰኞ ድረስ ዛሬ ወይም ነገ ነው።
ስለዚህ አክሰስ የሚያደርጋችሁ ማኑዋል
ለማኑዋል ነገር ካለ ነገሩ ይኖራል እነሱም ጋር ግን ቢያንስ ኮንሰርን ምን ላይ ኮንሰርን ማድረግ እንዳለብን ላቡን ስንሰራ ከእያንዳንዶቹ ውስጥ የሆነ ነገር ሼር ብታደርጉ በቴሌግራም ሊሆን ይችላል ወይም ደግሞ በኢሜይል ሊሆን ይችላል ሼር ብታደርጉ ቀጣይ ሳምንት ግን ከሁሉም እንትን የሆነ ሰመሪ ነገር ከሁሉም በጣም አቴንሽን ቱ ዲቴል መስጠት አለባችሁ ይሄ በጣም እንትን ያስፈልጋችኋል ለሚዛን ፕሮሰሲንግ የምትሉትን ሪቫይስ ቢደረግልን
Sure. Yeah, I think lab using background and then the discuss ማድረግ እንችላለን የሚያግዛችሁ ምናልባት ከዚህ በፊት ሰርተው ማየት ይችላሉ እና ነገር ካለ እንደዛ ቢሆን ማንኛውም
ድምጽ እየተሰማን አይደለም
I think እናንተን ሚውት ካላረኩት እኔም ራሱ ብዙ አይሰማኝም ሚውት ሳደርገው የኔ ይሻላል I don't know ኦኬ ነው አይ ቴክኒካል ስታፍ ልጅ ባገኘው አይ ቲንክ አንዳንድ ነገር ልነግረው ይችላል እንደዚህ አድርጓችሁ ስሩ ይሄንን እንደዚህ ነው የሚሰራው ብዬ ልነግረው ይችላል ነበር ምናልባት ከዚህ በፊት ሰርተው ማያውቁ ከሆኑ ኦልሬዲ ግን ፋሚሊየር ከሆኑ ማኑዋሉ ስላለ I think ላቡ ሆፕፉሊ ስሙዝ ይሆናል ብዬ ገምታለሁ
ላብ አሲስታንሱ ለብዙ ጊዜ የሰራ ነው እና እያንዳንዱ ነገሮችን ስለሚያውቅ ችግር የለውም ምናልባት ግን ለኛ እናንተ ኢንፎርሜሽን የምታደርጉት ነገር ካለ ነው እንጂ ላብ አሲስታንቱ ያው ራሳቸውን ችለው የሚሰሩ ናቸው ዶክተር አቡበከርንም የሚያሰሩ እነሱ ስለሆኑ በሱ ላይ ችግር ይኖራል ብዬ አላስብም ግን አንዳንድ መረጃዎች ሼር የምታደርጉት ነገር ካለ በቴሌግራም ወይም በእንትን ሼር ብንደ ስለዚህ ቀጣይ ሳምንት ክላስ ይኖረናል ማለት ነው በዚህ ሰዓት
ኦኬ ሪቪዥን
እናመሰግናለን
ኦኬ ዌልካም
Betul ya? Edit. Ya? Halo. Halo. Mesra ቤት ነው